Hello, my name is Konstantin Dmitriev, and I am a researcher at the Acoustic Department in Moscow State University. My report will mainly concern active-passive acoustic tomography in the case when the field in the medium is created by incoherent sources. I will discuss the iterative approach based on the coherence matrix processing and present the results of numerical simulations. The task of acoustic tomography is to determine the properties of a medium or an unknown object by measuring the field outside it. The usual scheme looks like this. There is an antenna array, and each of its elements either emits a signal or receives signals that have passed through the medium. As a result, the Green's function of the inhomogeneous medium is obtained. It can be converted into the scattering amplitude. A complete set of such functions serves as the basis for one or another algorithm for solving the inverse scattering problem. This is the so-called active tomography mode. However, in a number of tasks, active irradiation of an object is difficult. For example, in geoacoustic or ocean acoustics, this requires very powerful and expensive transducers. The solution is to use the intrinsic acoustic field already present in this media. It is created, for example, by surf noise, marine life, microseisms, distance shipping, and human activities. Thus, in practice, the problem arises of reconstructing the scatter in the passive mode, taking into account that the sources are incoherent. The passive mode is usually based on the correlation processing of the fields registered by the receivers. To solve the described problem, the method of noise interferometry is used. It is based on the fact that under some assumptions, the coherence function of the acoustical field is proportional to the difference between the retarded and advanced Green's functions. This means that by measuring the coherence function, it is possible, as in the case of active tomography, to solve the inverse scattering problem. However, these assumptions become difficulties for this method, and the most important of them is the required isotropic location of the sources. This case will be discussed in my report. Let's consider the acoustic field in an homogeneous medium. The acoustic field potential satisfies the Helmholtz equation, and here the primary sources of the field are on the right side, and the medium is completely described by the square of wave number k. The solution can be represented using such an integral, where g is the Green's function of the considered inhomogeneous medium. It satisfies the same equation with sources in the form of delta function. The scattering problem can be formulated as follows. Let's represent the function k squared as assume of some known background distribution k squared background and the addition minus epsilon. For example, the background can be a homogeneous medium, then it is just a constant. But in the general case, this is not all necessary, and the background medium may be inhomogeneous. Then the Helmholtz equation for the Green's function has the following form. We also write an equation for the function g background. This is the Green's function in the background medium. If the background medium is homogeneous, then the Green's function for it is known analytically. For the inhomogeneous case, it can be calculated. Combining these two expressions gives the Lippmann-Schwinger equation. It states that the total field in the medium is assumed of the incident field and the field scattered by all inhomogeneities. The equation allows us to solve the direct problem of determining the field in the medium. If epsilon is known, then it is simply a linear equation in G. It can also be used to solve the inverse problem, but it is much more complicated. We introduced three parameters which characterize the difficulty of solving the inverse problem. First of them is the maximum ratio between the scattered and incident field. Two more parameters are the norm of the scattering amplitude and the maximum phase shift, which is obtained when a certain beam propagates through the inhomogeneity. If any of these parameters are big, the scatter is strong and its reconstruction may face certain problems. The task of simultaneously determining the spatial power density of sources together with the characteristics of the medium seems to be extremely difficult. Therefore, in order to advance in its solution, several simplifications must be made. First, we will consider the sources to be incoherent. Then the coherence function is expressed as an integral of the unknown Green's functions and the source power density. Now, if the scatter is weak, we can write the Born approximation for Green's functions. Then the coherence functions turn out to be related to the inhomogeneity of the medium in this way, with an accuracy of the first order of the magnitude. It can be seen that the first term on the right side is the source coherence function, which would be recorded in the absence of inhomogeneity. Using it, you can get such a linear integral equation with respect to epsilon. And now it can be seen that if gamma background were known, then this equation would be similar in form to the Lippmann-Schwinger equation, and it could be solved similarly. To find gamma background, it is necessary to know the power density of the sources I, and in some problems it can be known. In this case, the reconstruction of homogeneity proceeds according to an iterative algorithm. Let there be an estimate of the previous step epsilon m minus 1. Based on it, the Green's function of an homogeneous medium is calculated using the Lippmann-Schwinger equation. Next, the background gamma covariance matrices are calculated using information about the power of the sources. Finally, a linear equation is solved for epsilon, and this value is added to the previous epsilon m minus 1 estimate, forming a new estimate. The loop ends when the difference between the gamma data and the gamma background falls below a certain threshold. Next, the following simplified situation is considered. Namely, it is assumed that along with the available unknown noise sources, there are controlled sources with known power in the medium. This corresponds, for example, to the case when the noise in the water area is created by a ship with coordinates known from the transporter. Another option is when controlled sources are created by the antenna array itself, as in active tomography. The difference is that they radiate noise and the waveform is not fixed. Different configuration of controlled sources provide different research angles. Separately, we emphasize the so-called zero angle when all the controlled sources are turned off. The difference between the field covariance function at the end and zero angles depends only on the controlled sources. The set of the research angles leads to a system of equations for the characteristic of the medium. It has the simplest form when each mu is represented by a single point source. Then a set of matrices U is registered in the experiment, which are equal to the product of the Green's functions of the unknown inhomogeneous medium. By writing these matrices in Born approximation, we obtain a system of linear equations with respect to epsilon, which can also be solved by an iterative algorithm. At the stage of numerical simulation, a measurement scheme with point sources located uniformly in the circle around the homogeneity was considered. It coincides in formulation with the usual mode of active tomography, which subsequently makes it possible to compare the results of reconstruction by different algorithms with the same input data. The difference is that narrowband noise sources are used, and it is the Q matrices that are recorded and not directly the Green's functions. The linear size of the simulated inhomogeneity is 5 wavelengths. The number of receivers is equal to the number of sources, and the number of them are equal to 20. The sampling step is 1/8 of a wavelength, and the number of receivers and sources is specially chosen to be small, since it is usually difficult to provide a large amount of data in an experiment. And it is interesting to see how scatters will be reconstructed in low element schemes. The two-dimensional inhomogeneity is specified using the function f and two coefficients, beta 0 and alpha 0, which determine its contrast in terms of sound speed and attenuation. In this case, the function arguments of the velocity and of the attenuation are reversed, which makes the shape of the inhomogeneity more complex. To analyze the results, two relative discrepancies are introduced. The first determines the scatter reconstruction error, and the second determines how well the reconstructed scatter satisfies the input data. The first simplified simulated inhomogeneity is given by the MATLAB function px. Its parameters are shown on the slide, and here is the dependence of speed on the sound speed on the coordinate. Due to the large contrast, despite the small size of the inhomogeneity, it belongs to strong scatters. It can be seen that the parameter m is greater than 1. Scattering norm and the phase shift are also quite large. Despite this, the proposed algorithm provides good reconstruction, as can be seen from the second picture, and the reconstruction error after several hundred of iterations is several percent, while the scattered field practically does not differ from the specified one. The situation is getting worse if we add a little noise to the input data. In this case, the discrepancy increased by almost an order of magnitude, and at an even higher level of interference, convergence may be lost. This instability is due to the fact that the scatter is strong and the amount of input data is rather small. If the number of receivers is increased, then the stability of the problem solution improves. Now I would like to discuss issues related to regularization in solving the problem by the iterative method. Numerically, the system of equation looks like a common linear system. When solving this system with Tikhonov regularization, it is required to specify the kappa regularization coefficient. To do this, let's consider the edging values of the matrix sorted in descending order. They are shown in the figure. It can be seen then starting from a certain number, they drop sharply. This number is approximately twice the number of source-receiver paths. The factor 2 arises here since the system of equations splits into a real and imaginary path. The kappa value can be chosen above the drop start level. For example, let's consider such a choice at the marked points 1, 2, or 3. They look very similar. However, the results of the iterations turns out to be significantly different. For point 2, the convergence rate is higher than that for point 1. However, for point 3, the iterations diverge. We have to be very careful when selecting the appropriate regularization parameter. It is quite difficult to make a choice. It is proposed to do otherwise. At the beginning of the algorithm, an initial rather large value of kappa is specified. At each iteration, it is multiplied by a gamma factor slightly less than 1. The result with this exponential decreasing factor is represented by the black line. It can be seen that the convergence rate is eventually even higher than that of point 2, and there is no plateau at the end of the graph. So this method seems to solve the problem. Another possibility of regularization is related to the special filtering of the solution. It lies in the fact that the components of the special spectrum greater in absolute value than 2k0 tau are assumed to be equal to 0. Tau is some multiplier that changes from 0 to 1. Then, at the beginning of the process, low special frequencies will be reconstructed, and then, already against their background, higher ones. It is assumed that this can increase the speed and stability of convergence. For example, the inhomogeneity of the Hausdorff shape, sound, velocity is considered. This is a pretty strong scatter. Moreover, its spectrum is concentrated mainly near 0. From the graphs on the right, it can be seen that adding filtering really speeds up the procedure and allows you to get an order of magnitude better result in this case. However, other situations are possible when the spectrum of the scatter is not concentrated at 0. Two inhomogeneities are considered in the form of a product of a Gaussian function f2 by cosine and by sinc. These inhomogeneities are noticeably weaker than the previous one. The spectra are wider than 2k0 and therefore they were appropriately filtered before the reconstruction. As a result, the spectra look as shown in the figures. The situation with convergence of iterations for these inhomogeneities is different. It can be seen that the addition of filtering in this case leads to the reconstruction error being close to 100% at the first iterations. Subsequent iterations cannot fully compensate for it, and the result is worse than without filtering. Therefore, it seems important to coordinate the filtering procedure with the expected nature of the special spectrum of the inhomogeneity. In conclusion, we would like to compare the results of the considered correlation iterative algorithm and Novikov's functional algorithm. For this purpose, inhomogeneities of the Gaussian shape were considered, and the parameter beta 0 for them varied over a wide range. When reconstructed with the Novikov algorithm, 1000 reception and emission angles were used. The graph shows the dependence of the relative discrepancy on the beta 0 parameter. It can be seen that the Novikov algorithm makes it possible to reconstruct scatters in a wider range of values of beta 0. At the same time, the results for negative values are much worse than for positive ones. Iterative algorithm makes it possible for to reconstruct scatters quite accurately at small values of beta 0. But for beta 0 outside this range, the stability is quickly lost and the iterations diverge. As a result, we can say the following. A method is proposed for solving the inverse scattering problem based directly on the covariance matrices without passing from them to the Green's functions as in the method of noise interferometry. On the one hand, it is not completely passive because controlled sources are needed. On the other hand, it is required to know only their position and power, and this expands the possible application of the method. For scatters of low contrast, the method provides a good quality of reconstruction, while the error increases sharply with increasing scatter strength. The considered regularization methods make it possible in some cases to improve the results of reconstruction. Thanks for your attention.